Okay, so now that you've seen the longest palindromic substring problem solved recursively, let's talk about the dynamic programming solution. So it's the same function definition. It just you pass in a string and you get the longest palindromic substring out. I've just printed it for ease of use. So we're going to call it on this O. So we still want that OTTTO as the longest palindrome. So the first thing that we do is we get the length of the string, and then we create a table, much like this table that I created before. We're just going to store this essentially in memory, and we're going to use it to basically save us calculations. So the first thing that we do, much like the recursive, and I'm just going to go through here and once the tables are created. A lot of that looping is it finding tables. So we'll find that. And it takes like a lot. There we go. Okay. So it takes a while just to create this table. And as you can see, that's, non-trivial, right? So I've got this table here. And then if you look, essentially this table is a n by n matrix. Okay. So what we're going to do is first, we're going to set the max length of our current palindrome to 1 because all the characters individually are palindromes. And we're going to go through the table and basically just mark all of the ones true. So you can see that happen here. That makes sense, right? Each index in this is an advancing position. But the length is 1, right? So each one of these, 1 and then 2 and then 3, these are start positions. So this first one refers to start positions, and the second index axis is length. So yeah, we change that and we go through and we just mark all those spots as true. And then once we're done with that, what we do is we have a start variable and an I, right? And so n is the length of the input string. So if the string at our current position, 0, is the same as the position next to it, then we set that in the table to true. So there's a couple places like that. We'll find it. It's this first one, ABBA. So we'll set that to true. So everything that has double letters anywhere, we go through and we find those and we just set them. So we're not doing anything super fancy here. It's going to take quite a few times to go through. Okay, so now we've gone and we've found, I'll go a few steps back, sorry. Hold on. It's a big problem here. So we've done this a few times now, and we've marked a bunch of things as true. And so you can see there's another true in here. Anytime we found a double letter, we marked that starting position as true. So now we're setting the starting index, and we're basically going to loop over the table again. Individually incrementing I and K, the length of the palindrome. So now the ending index, which we're calling J, that's that second corner. The ending index is K plus, or I plus K, the length of the thing that we're checking right now. And so right now, K is 3, right? So we're checking for palindromes of length 3. And that's -1 because, yeah, that's the ending index. And so that's a length 3. That's inclusive. I is the starting point, and then 2 over is 3, a length 3. So then we're going to check for the substring from the ith index to the jth index if and only if substring of I plus 1 is a palindrome. So we check our table here and we don't do a calculation. While k is 3, it seems really onerous to do this and just a little bit extra. But once k gets up to something larger than 3, we'll go through here until k gets a bit bigger. And we keep iterating I. Once j is at the end of the string, there we go, j is almost at the end. Okay, so now k is 4. Okay, so we set j to be 3, and that's 0, 1, 2, 3. So that's the corner of the second index. So now we're checking to see if the first letter and the third index, the fourth letter, are the same. So we check this, and we make sure that basically the letters inside are the same if the nearest neighbor index is true. So table at I plus 1 and j minus 1 and string at I and j. So that's basically everything on either side. So while k is 4, again, this seems a little trivial, but once k is a little bit bigger, it starts to really save us a lot of time. However, if you kind of look at the number of steps it takes in comparison to the number of steps the other code took, 200 steps or so, and this code takes 773 steps. Some of those steps are creating this table, but a lot of the steps are just going through and setting a bunch of things to be true, like the length 1 palindromes, etc. So we see that k is 4 here, but once we get to, like, I'm just going to skip way ahead, k is 5, k is 7, right? If we look at our table here, we found a number of palindromes. And if you look sort of towards the end where k gets to be much larger, you really start to find quite a few palindromes, right? We've got a table of all found palindromes indexed against their length. So down here, 13, that's not length 13, it's just position 13. But let's see, hold on. Yeah, basically, it just helps us to find the starting index. Sorry, let me just show you sort of towards the end. So max length, once we find something that's true and we set something true, this a palindrome at I and j, if k is less than or it's greater than the max length, we just set our max length and we set our start. And so basically every time we find one, we look at its parameters and we say, is this bigger than the largest one I found? But we don't have to check to see if something smaller is a palindrome. So that's really where we're saving those calculations. We've basically saved our recursive function call in a table here. But this is one of those examples where it doesn't actually really save you time or space. This is far less space efficient than the recursive algorithm. So dynamic programming is not always the way you want to approach things. It's not always a speed up to save space, or I mean to use space as a trade-off for time, because sometimes in the definition of the problem, essentially the recursive solution is fairly efficient and doesn't tend to go down paths that don't make sense. So yeah, this is one of those examples.